Anyway, so we will start slowly because I have a 4 hour. Okay, from in this afternoon I have to teach 4 hour. Okay, so I have to keep my energy here. Okay, 我们大概有今天有四个小时连续的课。Okay， 刚教完一堂课。Okay， 那 anyway， so here is one flow phenomenon. Okay, we call the starting voltage. Okay, on the wedge. Okay, this is so once you turn on the flow, like at the beginning we don't have, this is a wedge, and we flow. Once we turn on the flow, suddenly 我们突然把速度打开。Okay, so once you suddenly turn on the flow, you started the vortex or vortices. Okay, vortex will be appear here, and when the time increase, that our vortex will be develop into more and more, okay, and then our voltage and this voltage core here, okay, 我们的 voltage core 就是我们的涡流的中心 ，okay, you can see also moving downstream direction, okay, and this is even down until some a little bit, okay, far from this leading edge, as you can see, they will detach from this wedge flow, and once they detach, okay, once they far away a little bit, okay, you can see this is a starting vortex until this position. You almost will be detached from this wedge, and you can see a reverse direction of what a wedge flow appear. Okay, a reverse direction of a vortex appear here. Okay. So this is vortex, the flow is the counterclockwise. This is the clockwise direction. Okay, 它有一个反向的一个涡旋在这个地方突然产生。Okay, and based on this, okay, as you can see here, we will apply this into our what? Into our 2D L Fourier lifting calculation. Okay, as before I say, when you have once you have a flow over L Fourier, right, and then there's general lift, right? There's general lift, and this lift can be calculated as what is equal to rho v gamma, right? Lift equal to rho v gamma here. Lift equal to rho v gamma, right? Rho v gamma. And gamma is what? Gamma is the circulation, right? And from the Kelvin theorem, as you can see, if this is circulation here, okay, this is circulation here, we must have the vorticity inside, right? Vorticity inside. Okay. However, how do we, even in the invisible flow, you can see most of the 2D L Fourier lifting theorem, 所有的这些二维的机翼的升力理论 ，okay, 都 based on invisible theorem. Okay, they don't talk about the viscous at all. Okay, all the 2D lifting theorem all based on implicit potential flow theory. Okay, and how come the 2D L Fourier lifting theorem? Okay, they can generate the circulation, and then this circulation induce this lift. Okay, this lift, and then without any vorticity inside. Right, without any vorticity inside. So here is one of the explanation. Okay, they do it. Usually, okay, when you have the L Fourier at the beginning, okay, L Fourier beginning, you start and turn on your wind speed. Okay, very similar to your starting voltage on a wedge here. Okay, they will generate a starting voltage from here, starting voltage here. Okay. And this starting voltage, once the starting voltage is moving downstream here, okay, and they will generate what? Generate another direction of the vortex here, right? And these two vortexes, the circulation of vortices should be equal, okay. So if you do this closed loop, okay, and this closed loop, the larger area closed loop, you will see this is circulation is equal to 0. If you include this starting vortex. Okay, so this circulation will be equal to 0 because this circulation is cancelled because it's reverse direction. Okay. However, since this starting voltage already moved downstream, we were not able to see it. in the flow field anymore, right? So what we can do is we only can circulate this area or this airfoil near the airfoil. We call it near airfoil area, and do the circulation. And this circulation, we did get the circulation flow along the airfoil, and this circulation will contribute to our lift, even is in the invisive flow. Okay, even is invisive flow. Okay, so here is a kind of by using the starting vortex as a phenomenon. Okay, so if you do the near airfoil circulation, you will find this circulation. However, this circulation didn't mean inside. Okay, this we have a viscous flow, we have vorticity. Okay, because we can assume this is an invisive flow, still can have a vortex circulation here because of this starting vortex. Okay, so that's kind of the one of the, okay, when you're talking about the invisive flow, they don't have any vorticity at all, and how no vorticity, how do you generate the circulation? Okay, that's kind of the will become difficult to understand here. But based on the starting vortex here, okay, and we can generate the circulation here, and these two vortex should be cancel each other. Okay, so our upstream is a uniform flow and rotational flow, or downstream is uniform flow, also rotational flow. However, in near field here, we have a circulation. Okay, and this circulation will contribute to the lift. Okay, that's how to apply to the airfoil lift calculation from the starting vortex phenomenon. Okay, so here is a kind of from the in the aerodynamics. Okay, if you after this class you may take another course called aerodynamics, and aerodynamics will give you the lifting curves, lifting line theory. And this lift line theory is very easy. Okay, you can see we have this circulation here, and since our circulation is based on the Kelvin theorem, all this vortex line should be form a closed loop, right? Should be form a closed loop, or either end on the boundary, right? That's a two possibility. So here on the airfoil here, we assume there's a vortex line here, and our circulation is above near the airfoil here. We have gamma here. Okay, and this is our starting vortex. Okay, this is our starting. So we can form this closed loop. Okay, so according to this kind of we call the lifting line theory. Okay, if you see the airfoil, okay, this is airfoil. This is not a 2D airfoil. It becomes 3D airfoil. 3D airfoil means there's a finite length. Okay, 我们讲的三维的记忆就表示它并不是无限长的，它变成是有一个固定长度的。Okay, this is a 2D vortex, 2D airfoil. 2D airfoil that means in the span-wise direction is infinity long. Okay, 就是这个二维的记忆就表示它无限长的，对不对？ In 3D airfoil mean there's a section, okay, there's a length here in span-wise direction. We have a fixed length here, okay. So as you can see here, okay, we have a two tip vortex from this flow variation picture, and these two tip vortex can be used in this lift line theory. Give you this vortex here should be turned this direction, and this lifting line theory should be turned this direction. OK， 所以你可以看到这个地方两个 tip vortex， 对不对？两个 tip vortex， 一个是这样旋进去的，一个是这样旋进来的。OK， so the OK， and flow behind this airfoil area here, as you can see, our flow will be rotation like this and rotation like this. So inside this area is here. All flow is what? Is have downwash, right? Downward. So we call this a downwash. As you can see, we have downwash here. This is downwash velocity, W. Okay. So this is a downwash. The flow here will have this downward direction velocity. Okay. We go downwash. So flow in this direction, with behind the airfoil here, we have this flow. The flow direction has a vertical component. Okay, this is a vertical component, velocity component here. Okay, we call this a downwash. Okay. Let me ask you one very interesting question. You may know. You see the bird when they do the long distance travel. Okay, they migrate from the North Korea to Taiwan. There's one called season bird. Okay, how do we call that? Black face spoon, right? 黑面琵鹭. Okay, all these birds they travel very long distance. Okay, and once they want to travel very long distance, they kind of form a spatial flying pattern, and this flying pattern like this, right? This is bird flying pattern. 我们中国古时候不是有一个诗什么人字的雁，对不对？人字雁。Okay, this is kind of okay. And why do they want to fly this like this? Why do they want to fly this pattern like this? Do you know? Huh?
因为它如果它这样的话，它每一只鸟的翅膀会产生挺多的。如果它拍这个形状的时候，它这个就会被缩小。
什么被缩小？
应该讲说它的这个挺多的就会被打乱，就是它不会再出现这么大的一个特别的。
Okay, that's your explanation. Okay, his explanation is okay. If we find this pattern, or the tip vortex here will be attenuate. Okay, become less strength. The tip vortex will be disappear and less severe. Okay, attenuate mean okay, but it's probably not. Okay, this is not the right answer. If you are bird, okay, you will know. Okay, but you are unfortunately we are not bird. Okay, as you can see here, based on this theory here, right? Each bird here we have the tip vortex, right? This tip vortex. So this is a flow, and bird there's a tip of a wing, and this tip vortex is rotate like this, right? Rotate like this. And I just mentioned behind this area here is what? There's a downwash. If your bird is flying behind one bird, what happened they will experience? What kind of flow they will experience? I flow and I have always the flow, downward flow is acting on me, and I have to fly even harder in order to generate lift. So I will fly very hard, okay? I will consume a lot of energy to overcome that. However, instead of flying here, I would like to fly here because if you are a bird, you will know. If you were a bird, you will know. 这要用假设语气。If you were a bird, you will know. When you fly out until this region, what happened? Because our tip vortex rotate like this, right? Rotate like this. So there's a downwash, there's upper wash here, upper flow here. So if you are a bird here, you will experience the upper lift motion, the velocity. Reduce your energy. Okay. So here our bird will be flying, okay, outside, okay, these regions to generate, okay, more lift with less energy. Okay, that's all because of this tip vortex. Okay, 这些 tip vortex here. Okay, so here we have our bird flying here. We can generate lift because the leading bird will be the most harder. The leader have to consume most of energy because they don't have any lift. So this leader, they will switch sometime. Okay, sometimes this bird will leading, and later time the other bird will leading. Okay, not always the same bird will leading. This. Okay. Anyway, this is a side story about when you see this. Okay, this tip vortex, and this tip vortex will give you a lot of information for it. Okay, and here's another issue. Okay, we just mentioned, okay, the circulation can be generated from 2D airfoil under the implicit, right? implicit. However, I also mentioned most of vorticity from what? From the boundary layer, right? Most of vorticity from boundary layer, from the boundary. Okay. So here is kind of one of the theorem or the corollary. Okay, one here. If a rotational flow, okay, your flow will remain irrotational, because you can see if my flow element here is irrotational, and my flow element here is also irrotational. What happened? Why? Because inside the flow field, I will not able to generate any vorticity, right? Vorticity can be increased if you are original have vorticity, right? You can increase by changing your moment inertia or changing the area. However, if you don't have any vorticity, you don't have any vorticity later. That agree. Okay? So because within the flow field, we are not able to generate any torque on the flow particle. Okay? So here, most of the time, if you have flow particle here, it's irrotational. If you this flow particle moving downstream here, still remain irrotational. So irrotational upstream, irrotational downstream. Okay, so that's the first thing here. However, on the boundary is different, right? Boundary, near the boundary. So all the flow phenomena will be generated from, very tricky from the boundary. We call the boundary layer. So there's one specific course called the boundary layer theory. 有专门一堂课 ，OK， there's one course here, OK， since it's lectured by Professor Miao, OK， Ch3 Miao is a boundary layer theory. This special course, OK. Okay, there's a full semester we're talking about boundary layer. Okay, because the boundary layer is so important for the flow field because a lot of disturbance vorticity is generated from the boundary. Okay, and the boundary layer is such thin. Okay, if the Reynolds number is much greater than 1, okay, this is a non-dimensional number called Reynolds number. Okay, later I think you know already, but later we will also give you what's the Reynolds number. Okay, so if the Reynolds number is much greater than 1, 你雷诺数很大的时候 ，okay, for this kind of flow, we can see the flow field, okay, can be divided into two regions. Here is this thin layer region, okay, so we call the boundary layer region. So the first region is called thin boundary layer region, near the wall. Okay, so this near the wall here, we have the boundary layer. Okay, and outside the wall here, outside of this boundary layer, we have the irrotational flow. It's almost, there's the outside the boundary layer, and the friction force is negligible. So for the high Reynolds number, okay, only the high Reynolds number. Low Reynolds number means the boundary layer will be thick. Okay, high Reynolds number means the boundary layer will be very thin. Okay, and this high Reynolds number here. So Prandtl, this is in the 1907. Okay, he proposed this kind of idea. Okay, because near the boundary inside the boundary layer, very complicated. Okay, and so a lot of the phenomena, okay, will be happening in the boundary layer. However, we may not need to know the basic, very detailed boundary layer, but we can still using the outer flow to do some of the engineering application. And later I would like to emphasize this. Even we didn't know the boundary layer information, okay, but still we can do the outer flow information and then get the engineering application too. Okay, so Prandtl in 1904, he kind of separated these two regions for the high Reynolds number flow. Okay, they can divide into thin boundary layer region and outer, okay, so-called frictionless region or the irrotational region. Okay, and by kind of divide into these two regions, by deal or handle these two regions different. Okay, and then we can get some engineering application later. Okay. And out of the flow here, since it's not influenced by the viscous effect, because only the boundary layer region there's a viscous effect. then alter the flow here, we don't have any viscous effect. We can neglect the viscosity. So for the outer region, we can neglect the viscosity, and we can also assume this is irrotational flow. Okay, there's no vorticity. Okay, only the vorticity is inside the boundary layer here. Okay, because the hydrogen sample, the boundary layer, the vorticity generated from the boundary all confined inside the boundary layer. Okay, outside this boundary layer here, outside region here, we can assume it's a irrotational flow. Okay, and once you assume the irrotational flow, we can assume our velocity field is a potential flow. Okay, so this is a potential field. So we call the velocity potential. So velocity can be represented as a potential. Okay, velocity potential by the gradient phi here. Okay. So later in the chapter 4, we will go into this. Okay， 在下一章我们就要讲这个地方。Okay, this is so we in the outer region here. Okay, flow over any object. In the outer region, we can deal with the so-called potential flows. Okay, and once you get the potential flow information or potential flow give you the velocity field, give you the pressure field. Right? 你可以去解这个 potential flow. You can solve this potential flow equation, Laplace equation, and give you the velocity potential, right? And then velocity field by take a gradient of this. And through the Bernoulli equation, later I will prove that. I will give you the Bernoulli equation. From velocity field, I can transfer to what? To the pressure field, right? Because the relation between the pressure and velocity can be related by the Bernoulli equation. Okay? So I have the velocity field and pressure field through this potential flow. And all these potential flow result can be used or cannot be used to predict the force acting on this object or not. Because in the past, okay, for the first one to study this problem is very near World War II or World War I, right? Because 1907, 1904 is 世界大战，第一次世界大战的时候 very near the World War I, right? And World War I, in the 1907, 03, we have the first human flight, right? 1903年 okay, Wright brother, okay, has a successful flight, human flight, right? That's 1903. Okay, 1903年我们第一次人类有一个飞机的飞行。So from that, okay, we start to go into the very theoretical work. Okay, and the physical problem is hard. How do you design the airfoil here and generate enough lift, right? Generate enough lift, and then can have a human. Okay, this lift can support the human weight, for example. So they would like to know that when the flow over any object, how many force will be generated, right? 那个时代就工程问题，就是说流体流过一个物体，你能产生多少升力，就是。Okay, so in order to solve this problem, and then so Prandtl kind of give this idea. Okay, we can separate our flow into the boundary layer region flow and outer region flow. And outer region flow is easy one, right? Because this is potential flow. And potential flow has, later in the chapter 4, I will show you, there's a lot of theoretical work. Okay, and you can use a piece of paper and pencil, you can write down all the equation and calculate all the lift. Okay, through the potential flow. Okay, so we can use we don't have any computer yet. Okay, at that time, 在那个时候还没有任何的电脑，对不对？就只有一张纸、一张笔。Okay, we only have one piece of paper and pencil, and try to calculate flow over any object. How many force can be generated, especially lift. Okay, so that's the main issue for that time. Okay, so by solving the outer flow region, because we separate the boundary layer region and outer flow region, it can assume this is a potential flow. And this potential flow can be solved, and pressure field can be solved. And pressure field here can be integrated, right? And the one question rest. 下一个问题就出来了。Okay, if you have an object, this is L4 here I have, okay? And we know there's a region here. There's a region here. Okay, this region here is the boundary layer region. Alright, this boundary layer region. And outer region here is the outside. Okay, we have a potential flow region. We can solve this equation. Okay, and solve this equation, you can get the velocity field. Okay, from velocity field, you can get a pressure field. Okay, and once you have pressure field, you have the pressure here. Pressure here. This is all pressure distribution and outer field. I can calculate the pressure field along this surface here from outer region here. Right? This is I can calculate from this flow, potential flow, and give you the pressure field. And there's a small gap here. But pressure field at the outside the boundary, and pressure field on the surface is the same or not? That's a question we have to answer. Right? I just calculate outside the boundary only. Outside the boundary is this. And then pressure at this location is on the surface. This is inside the boundary. And so is this pressure, yellow pressure and the white pressure, is this two pressure the same or different? 大家知道是一样还不一样？一样的就是 if this is the same, is that same? Okay? Is that different? Okay? We kind of go back to 1907 or 1904. Okay, to discuss this question. 我们回到古时候想要回答的问题。有人认为一样，有人认为不一样。到底一样不一样 ？Okay, that's in ancient people they discuss this like us. Okay, 古时候他们也在讨论这个。In order to answer this question, we already have answer. But in order to give you the right answer, we have the one homework, okay, for you to study. Okay. Since this chapter is beyond our lecture note, okay, beyond our lecture note, because our lecture note don't have this chapter. Okay, we only have until chapter 7. Yeah, I remember. So in the chapter 9, okay, in the IGQ textbook. I don't know if you have a textbook, but okay, I have a PDF file for this textbook. If you don't, okay, I can cut this section for you. Okay, if you don't have this, you cannot find it. But try to read this. In the chapter 9 is related to the boundary layer. Okay, so the boundary layer is what? It's a Professor Miao will teach that. So okay, that's the other course. But however, in order to answer this yellow pressure and the white pressure, is the same or not, we have to know a little bit this. So only the section, chapter 1 to chapter 9.1 to chapter 9.2. Try to go back to read it. Okay? So and here in this two chapter 9.1 to 9.2, they will develop so-called boundary layer equation. They will simplify our Navier-Stokes equation, right? Simplify our equation, apply to the boundary layer. Okay, that's in the chapter 9 they are doing. And try to read it because we already introduced the Navier-Stokes equation. And through the scaling issue, okay, you can derive the boundary layer equation. And the answer is we have x momentum equation and y momentum equation, right? And energy equation. In the Navier-Stokes equation for the boundary layer equation, we have x momentum and y momentum equation. And if you check the y momentum equation, you will see